So again, to review, principle of original horizontality says that no matter what they look like today, they were born in nice flat layers. Now I keep saying no matter what they look like now, they were born flat. What do I mean what they look like now? What could they look like other than this? Now they could be broken, that's one thing. But what are some other things that these whole huge sheets of rock could do? Yeah, they could do that. I'm talking about they're still looking like layers, but not flat layers. We talked about this yesterday. So they could, remember, if they slam into another plate that looks just like them, what's one thing that they could do? They could tilt. So they could now look like these crooked layers. But all that original horizontality is saying that when they were born, they were nice and flat. Another thing that they could do, and I'm going to just grab some not as perfect layers because it'll demonstrate it a little bit easier. Because I don't want to mess up my perfect ones right now. So there's another set. So we could tilt them. Another thing that could happen is they could bend. But again, all that original horizontality is saying is that when they were born, they were nice and flat. Now, why is it helpful to know they were nice and flat? Let's say they were born this way, vertical. What can I not do that we talked about yesterday? Now that they're vertical, what makes it, what's a little bit more difficult? If they were born this way, what can I not talk about then? Okay, well, definitely being flat. So let me actually, maybe I'm asking the question wrong. Yeah, the age of the rocks, thanks. So when they're flat like this, I know which one's the oldest, right? So which one is the oldest from what we did yesterday? The bottom one. And the bottom one has, because you can't build layers, you can't start from the top and work down. I have to start with whatever's down first and then pile stuff on top of it. I can't work from the top down. Just like if you ever tried to build a pizza, starting with pepperoni and then working down, can you make a pizza starting with the pepperoni, then going to the cheese, then the sauce, then the crust? You can't. You have to start from the bottom up. So what I was getting at then is law of superposition tells us the oldest one's on the bottom, the youngest one's on the top. That only works if they're horizontal first. If they were vertical, which one came first? You don't know. You can't tell. So these two principles, they're buddies. You can't have one without the other. You can't tell me which one's oldest if they weren't originally horizontal. Now, faulted strata, we said, is when rock layers get broken, and they get broken by plate tectonics. And I got to take them apart because you guys know the stress this Play-Doh is causing me. Hang on. Remember, in real life, they don't get taken apart before they break. Only when you're using Play-Doh. So now that the rock layers are broken, they can move apart. They could smush together. They could tilt up like this. They could do a bunch of stuff now that they're broken. But one thing that's important is once they're broken, even if they were miles apart, you can still match up. This bottom layer matches with that bottom layer. This yellow layer matches with the yellow layer, and the blue layer, top blue layer matches with the blue layer. So plate tectonics can break them, spread them apart, and it could squish them together so they end up like this. Faults can do a lot of things. But one thing I wanted to talk about is, now that there's a break in the rocks, is the break younger or older than the rocks? Think about think about this, everybody. I broke the rocks. You thinking about this? I've broken rocks. What's older, the rocks or the break? What's older? Think first, don't shut anything out. What's older, the rocks or the break? Trent, you thinking? What's older, the rocks or the break? Rocks. How? Why? How did you say that so confidently? Say it louder. You can't break a rock without the rocks already being there. That's kind of common sense, right? So whatever gets broken had to already be there to get broken. So this goes along with this putting rocks in order of their age. So now I know, okay, yes, this bottom layer was first, then the yellow layer, then the top layer, then the break. So you can still put these in order. Remember how we talked about relative age last week? Putting things in order. I don't know exactly how old each one is, but I know that this blue layer is older than the yellow layer is older than the blue layer, and the break is younger than everything. This is what we're going to be doing for the next week. And there's a lab on it. So putting things in order. The last two vocab words we had were intrusion and extrusion. Do you still have the reading? You should, you're right. Good answer, you should. Go back to the reading and find intrusion. You should have highlighted it or underlined it. Do you have it? No, who do you want? You don't have yours from yesterday? Oh, it's page 15 then. Sorry, other way. Did you find intrusion in there, Carter? Did you find intrusion? No, you don't have an underline from yesterday? Do you have the reading? Okay, you got it, Brendan? All right, go for it. Why don't you just, an intrusion. Perfect. So we can sum that up. We don't need that whole sentence. Hot magma squeezes between rock layers. I'm actually going to add another 2 lines, so hopefully you left enough room. Hot magma squeezes between between rock layers. Go back to the reading. Keep reading. What does it cause? Yes. Causes contact and you can go into this other box over here. Causes contact metamorphism all around intrusion. And we're going to talk about what contact metamorphism is. We already did in chapter 3, but you're going to need your brains refreshed. Do you guys remember whose shoulder I burned when I talked about this? It was you. That's what I figured. Michael, you're going to get it today too. All right. Michael and Jake are going to be rocks. They're going to be sedimentary rocks. Jake's going to be a pile of limestone. Michael's going to be a pile of sandstone. I'm hot lava. Hot, molten, liquid, burning lava. And I'm going to squeeze my way in between the two of them and touch their shoulders. What's happening to their shoulders? Burning. I'm changing their shoulders. I am burning it and changing their shoulders into a new metamorphic rock. What's happening to Shelby? Is she? Shelby, how are you feeling over there? You affected at all by this hot lava? No, I'm not touching her. She's fine. Jesse's fine. How are their feet? How are Jake and Michael's feet? Fine. Why? Not touching it. Only thing I'm touching, their shoulders are the only things getting burned. So when hot lava squeezes up through the rock layers, it's going to do the same thing I just did to Jake and Michael. It's going to burn whatever it touches. But if there's a layer it doesn't touch, like Jesse and Shelby, nothing happens to the layer it doesn't touch. So I got to do a little bit of rearranging of my layers. Give me a second. some off scenes maneuvering here. Of course, I did put that close enough. All right, what we got going on? I'll just move it up here. So we have our rock layers. We got the same original blue, yellow, and blue again. Lava is going to come up between these layers, just like I squeezed in between Michael and Dave. What's that lava going to do to all the layers around it? Burn it. Change it. Now, officially in rocks, it's not called burning, but it works in my brain to think of it as burning. And think of it, if you burn a marshmallow, doesn't that marshmallow where it gets burned completely change? Goes from being white and fluffy to black and charred, the flavor is completely different. Same here, the rocks are going to be completely different where it touches. So it's going to burn it. So in our drawing, so don't draw this yet, I'm going to have you, so we've got all these rock layers and the lava has squeezed up. On the regions, I need a black. On the regions, they're going to show this. They're going to show this burning with, I call them little whiskers, but anywhere where that lava touches the rocks around it will burn it. And they demonstrate that burning with these little whiskers. So any rock layers that were there are going to get burned, and they're going to show it with these little whiskers. That's where they demonstrate contact metamorphism. So we need to add this drawing that's very similar to, of course, now that's in the way. So we need to do a drawing that's similar to this picture. So how I go about this is I draw still my same 3 layers. You might want to wait till I'm done and then you can copy it. And one of my layers was shaded so I could demonstrate it was slightly different. And hot lava squeezes up. So that's the lava, and I still have to show my contact metamorphism. So you still need to include those whiskers. So anywhere that lava is touching gets those little whiskers, and those whiskers are contact metamorphism. And I am just going to label my rock layers. I have rock layer A, B, and C, just so that we can talk about them. You don't need to include the A, B, and C if you didn't already. I just want to talk about them up here. This is how the Regents is going to show it with the whiskers. Now I got a question for you, and I don't want anybody to shout it out yet. Think first. So here's my layer. A is on the bottom, B, then C. First of all, what's the oldest rock layer? Is it A or C? Which one's the oldest layer? A, B, C. A, why is A the oldest? Because it's on the bottom. Then B, then C. But what about the intrusion? Where does that fit into it? Is it older or younger than layer A? How do you know it's younger? So, but hey, I want everybody over here paying attention too. Braden, this is still right up your alley, okay? You answered the last question right. I bet you can do this one right. How do I know that A is older? Go ahead, Brendan, you were going to say something. So one, for the lava to get in between the crack, it had to be there. But there's also another key thing that goes right along those lines. Not necessarily because it goes above it. That's kind of a trick. Yes, kind of, but there's something else I want you to notice. What's going on with A that proves A had to be there? The touching point. When I touch Jake's shoulder, he had to be there already, right? If I'm hot lava squeezing in between here, and then I touch them, don't they already have to be there? I can't touch something that's not there. I can't burn something that's not there. So for the lava to burn or change or contact metamorphosis, that didn't come out right, but to cause contact metamorphism, the rock already had to be there. So then, now everybody think of this answer in your head. No one shout anything out. How about layer C, the one on very top? It's on the very top. Is it younger or older than the intrusion? So don't say anything yet. C, the one that's on the very top. Is it younger or older than the intrusion, the black, the dark, solid ones? I don't want to call on anybody because I don't want to put anybody on the spot. Does anybody want to volunteer an answer? What's older, the intrusion or C? Nobody's going to try this one? How do you know C is older? How do we know C is older than this intrusion? Okay, you can say that it's already there, but you got to tell me how you know it was already there. Because why? I just couldn't hear you. So Shelby's right. C is older, and whoever added because it was already there is correct. But the Regents is going to ask you, how do you know C is older than the intrusion? And you have to be able to put it in words. The whiskers. Braden, you got that? I know that C is older because it got burned by the intrusion. So the little whiskers, the little marks tell you that it got burned. To get burned, you already had to be there. That is a concept that you're going to have to understand and be able to reproduce exactly what I just asked you. First of all, which one's older, the layer or the rock? And then you got to tell me how you know. Because it got burned is how you know it was already there. All right, extrusion. Last thing on here. Similar to an intrusion, how is it different? It does, but what's different between an intrusion and extrusion? Because both intrusion and extrusion cause contact metamorphism. No, they're similar. Everyone go back to extrusion. What'd you say? Lava makes it to the surface. So in extrusion, hot magma squeezes through rocks and makes it to the surface. So it's really, really similar to an intrusion, except it doesn't get stuck in between layers. It makes it to the surface. Basically a volcano, right? Lava comes up and spews all over the surface. So I could take my same, almost my same thing here. And I just removed the top layer. And now that's an extrusion. But we got to talk about the lava burning again. So I'm going to draw a very beginnings of this one. If you want to wait till I'm done, you can. And the lava makes it to the surface this time. So it's basically the same exact drawing, except for I'm missing the top layer. If you want to draw something similar to that, we got to talk about contact metamorphism now. So once you get the drawing, I'll stop and wait, see if you got any thoughts on the contact metamorphism. As long as you see. So guys, make sure on that last drawing I'm looking on, I don't see whiskers on everybody.
Does yours have whiskers?
We're gonna talk about it. But the last drawing, so the intrusion one, make sure you have those whiskers. That's like one of the most important things that I just talked about. Now let's talk about the extrusion. Does it have any whiskers? Does it burn anything? So it's still squeezing up, still hot lava. Does it burn anything? That was a question mark. What do you guys think? I'm gonna talk to Riley in the middle here. Riley, what do you think? Does this hot lava burn anything? Anything it touches. So the layers below is exactly right. So this hot lava's sitting on the ground here. It's burning these layers below it. So it's burning there. Same deal when it came up through the ground, it burned these. So add those burn marks. It burns everything it touches. But there's one key thing that's missing. Where is it not burning? Yeah, up here, there's nothing to burn. So it's bald. The extrusion is bald. No whiskers on the top. Make sure your picture looks like this. You have to include the whiskers. But now, here's the thing. Well, I'll wait till you guys are done drawing. Now, we've got our volcano that has spewed all of its lava. What happens to that lava?
Just pop it in and say hi.
Hi.
Somebody back there too, say hi.
So this volcano has spewed its lava all over the place. What happens to that lava? Come on, this is chapter 3. What happens to lava, guys?
It solidifies.
It cools, hardens, turns into igneous rock. We don't know which one, but it's igneous. And now it's sitting there as a hard, cold rock. What might happen on top of that hard, cold rock? More layers. We might get more sediments deposited on top of it. And now it might look like this. Million years later, it looks like this. So in my drawing, there might be another layer on top after a couple million years. But does this layer get burned? Doesn't tell me. Why does it not get burned? Yeah, it's cooled. It's not hot anymore. It's nice and cooled off. So this new layer does not get burned. So do I add the whiskers? No whiskers. So then, now this is buried. It's in between layers now. Does it now change to an intrusion or is it still an extrusion? It's still an extrusion. It gets named by how it was when it was born. So this is still an extrusion. So if you saw these two pictures, which is what the Regents is going to do, they might give you this one or they might give you this one. They're going to ask, is this an intrusion or an extrusion? It's not an intrusion. No, no, no. The only way you can say it's an intrusion is if it was born an intrusion. So you can't just look to see if it's buried or not. You look to see if it has whiskers. With an extrusion, it will be bald on the top. So we need to add that to our notes. Only contact metamorphism on the rocks that were there. when it formed. I'm gonna add naked on top. Maybe I should have said bald. So you do have to be able to tell the difference between an intrusion and an extrusion. The very last thing they're going to ask you, again, you don't have to label these, but if I had rock A, B, C, and my extrusion, again, don't answer this out loud yet. What's older, C or the extrusion? Now in this new one, C or the extrusion, what's older? What do you think? Extrusion? It is. The extrusion this time is older. Here's the kicker. You got to be able to tell me why. How do you know that the extrusion is older than C? You want to give it a whirl? The lava was cooled and hardened that got put on top. But you got to tell me how you know that from this picture. What's missing? Because it was cooled and hardened, what didn't happen? It didn't do what? It didn't what? It didn't burn it. So it didn't change it. So you got the idea there. You knew it was cooled and hardened and dried, and so then it didn't burn it. Okay, so we got the basics of this. We're going to do some practice with this tomorrow. What I realized is I forgot a whole page of notes. I don't know what happened. Like the whole page is missing. So we're just going to shorten it up and everybody has a blank page 22. So some of you have two, those of you with the double-sided packet, you just have a blank page 22 and it even says 22 on the bottom. Those of you with the single-sided, it's just one of your blank sheets of paper. But it does say 22 on the bottom. And there's just a few vocabs that we have to add to this. It's going to be about a half a sheet's worth of paper. So you just kind of can judge it on how. So you have that much room for me. So that's how, like, you can judge how big to write. You don't write ginormous, but you don't need to write teeny tiny. All right. So we're going to start. Wait, I got to share the screen. Oh, I lied first. Oh boy. You guys got to do homework because you didn't have it yesterday. Your homework is page 18. Write that down. Everybody take a minute. Go to wherever it is you write down homework. Homework. Page 18. There are 4 boxes. Pick 2. Seeing some people writing that in some pretty weird spots. So your homework is page 18. It's these 4 boxes. Whoa, where'd that go? Oh, struggling. Stop share. Page 18. Pick 4 of these. No, pick 2 of these. Whichever 2 float your boat. Okay? You can remember that? So you guys write it in some weird places. In case you ever forget if there's homework, you guys remember I posted on Teams, right? It's always there. You could also always message me. I'll tell you if you forget. All right, now go to page 22. All right, we'll get done what we have, what we can. We might not get it all done today, but we'll do our best. We're gonna move too far. First thing we're gonna do is rock correlation. So you can, that's basically the first definition. It's also the title of these notes. So you should have rock. We already talked about this, believe it or not, but my third period class couldn't remember it. Alfred Wagner, he correlated mountain ranges. He correlated fossils. He correlated the rock layers. What did Alfred Wagner do when he correlated all of that stuff? Hint, it's up there on the board. He matched up the rock layers. So he saw a layer over here in Africa and a layer over here in South America. And he's like, oh my gosh, those are the same layers. So correlating or rock correlation is just matching up the rock layers. I have a perfect picture that shows this. Here's a picture of the Grand Canyon. And in the Grand Canyon, I'll turn up the lights so you can see it a little bit better. What I wanted you to be able to see is the Grand Canyon it's mostly reddish, orangish colors, but if you look closely, you can see, well, here's a red layer, there's a white layer. Same here. Here's like a brownish layer and there's a white layer. The Grand Canyon is separated, the rock layers are separated by the canyon. So there's this big gap. But take a look. This white layer right here, even if you follow it through the gap, matches up perfectly with this white layer. They're the same rock layers, even though they're separated by a big gap. Same up here, you can see this red section here, separated by quite a big red gap, but matches up perfect with that red layer. And it does it for all the layers, you just can't see them as perfectly on this picture. And this does this for not just the Grand Canyon, but most of Arizona and Nevada. If there were rocks there, you'd be able to follow them all the way across the state. I think it's kind of cool. You can do that around here if you're walking in the creek and you, if the creek kind of goes down into like a valley and you can find the layers of shale on the wall where you're walking, you could actually follow one layer of shale all the way across the creek. Pretty neat. So that's rock correlation. The next one is an outcrop. So an outcrop's the next vocab word. This is exposed rock layers, meaning they're exposed at the surface. Sorry, I know I'm in your way. And remember, rock layers are also called strata. So remember, we've talked about bedrock. Bedrock is that solid rock that you hit after you dig through all the dirt on Minecraft. Well, anytime that there's no dirt to dig, but there's still solid rock, so here, or mountains, or the Grand Canyon, there's no dirt there, that's still the bedrock, and now it's exposed at the surface. That's called an outcrop. Again, you can follow those layers. See, here's that nice white layer all the way across this set of rocks here. And now we're going to move on to the last thing I want to do for today, index fossils. Do those sound familiar? When did we already talk about index fossils? Yesterday, a little bit in lab 2. I actually started talking about them last Wednesday. Where can we look up index fossils? On the what? You could. But since we don't have the internet, we could look right there. Bottom of page 8 and 9 of the reference table, they're even labeled index fossils. Going back to what we did on Wednesday, the little bit that you needed to remember is these guys. The letters down here match up with the letters on the page 9 of the reference table. Remember those? Well, actually, so here, let's go this way. So an index fossil, so you can write that, it's right at the top. An index fossil is a geological time marker. And that's one thing we mentioned, or I mentioned last week, is that these guys on the bottom of page 8 and 9, they were only around for a little bit of time. They're only around when their circle was there. Yeah, that circle takes up about 10 million years or so. And that sounds like a lot, right? 10 million years. So I know 10 million sounds like a big number, but in terms of the whole Earth's history, 10 million is not that much time. So it's only around for that short period of time. So anytime you find one of these, like if I found one of these letter A's in the dirt I was digging up, I know that that is from the Middle Cambrian time. So it's like these guys are basically time stamped. Like, you know, when you take your picture and it's got the time in the corner sometimes, that's basically what these fossils are. They are saying, if you find one of these, I know when it's from. And here's the last thing we're going to do for today, 3 things that make a good index fossil. Not all fossils are index fossils. To be considered an index fossil, it has to be easily recognized. Easy to recognize does not mean easy to find. But it means if you pick up one of these, you could look at a chart and you can see its distinguishing characteristics and say, oh, that's one of these. That's letter A. Live for short geological time, so only a couple million years. And spread out all over the country or all over the whole entire state. This is where we'll pick up tomorrow. Again, you guys have homework on page 18. It might take you 5 minutes. Don't lose points by not doing a 5-minute homework assignment.